Okay, this video is about improper integrals. First we're going to discuss type 1 of improper integrals, and that's when they have to do with infinite integrals. So, if we begin by remembering a definite integral, let's remember what that looks like. So, let's suppose we're integrating from a to b some function. So here's my function f, let's say, and let's say this is my a and this is my b. We're integrating under the curve from a to b, and so what we're calculating with this integral is the area under the curve from a to b. So that means this is what we are calculating, that area right there. So what happens if we change one or both of these limits to infinity? What happens there? So let's consider this. We've got the integral from a to infinity, f of x dx. Okay, this is an infinite integral. This is improper, but what does this mean that we're trying to do? We're trying to integrate under the curve from a to infinity, like and beyond, right? So instead of calculating this area, we're looking at all of this. Okay? Will it converge? Will it diverge? We have to try to figure that out. Here is the second one. What if we decide to integrate from negative infinity to b? All right? So here's our b, and basically we're looking back here as far as we can go. So we're trying to say, hey, will this all, if we go on forever in the negative infinity, can we calculate that area? And then the third one under type 1 that we get is from negative infinity to positive infinity. Oh, here's my f of x dx. I meant to put that on there. F of x dx. What this means is we're just integrating everywhere under the curve, as far to the left and to the right as we can go. All of this area. Is it possible to calculate the area under the curve in both directions forever? So, it may diverge, which means we can't get a number out for that. Or it may converge to a value, and we say, oh, this is the area as it goes on infinitely in this direction or that direction or both. So, the way we handle this is with infinite limits. We can rewrite this integral into an infinite limit like this. We say this, we will consider this to be equal to the limit as t approaches infinity of a to t f of x dx. In the second case right here, we would say that this is equal to the limit as t approaches negative infinity of t to b f of x dx. Okay, and what do we do here? Well, what we do here is we pick some value c in between negative infinity and positive infinity. So any real number will do, because they all fit in the category between negative infinity and positive infinity. So we pick some value here, c, and we break up our limit into two. And so we say this will be approximated by a limit. The limit as t goes to negative infinity of t to some value c somewhere on this integral, f of x dx plus the, oops, I forgot my limit, the limit as t goes to positive infinity from c to t of f of x dx. So first thing we do is we rewrite the improper integral that we're working with. Second thing we do is we evaluate the limit. If the limit diverges, the integral diverges, we cannot find the area. If the limit converges to a value, then the integral converges and we can calculate the area and we can find that number. here, in this case, where we have both two limits, if either one of these limits diverges, then the whole thing is counted as divergent, and we can't find its integral. Okay, so that's how that works. So let's look at a few examples here. The first one that we'll look at is try to calculate, determine if the integral from 1 to infinity of 1 over x dx is convergent, divergent. If it's convergent, what value does it converge to? So, the first one. Integral from 1 to infinity of 1 over x dx. Okay, first we'll rewrite it as a limit. We'll say this is equivalent to the limit as t goes to infinity of 1 to t of 1 over x dx. Then we will integrate this. Okay, the integral of 1 over x dx is the natural log of x. And so we're going to integrate it from 1 to t, and this is the limit as t goes to infinity. All right, so let's evaluate it. This will be the limit as t goes to infinity of the natural log of t minus the natural log of 1. Well, the natural log of 1 is 0, so we're just considering the natural log of t. But if you think of a logarithmic graph, it starts off here and then it increases. But as x approaches infinity, it continues to increase. So as we put the natural log of infinity is going to be infinity. So this diverges, so that therefore we say that the integral from 1 to infinity of 1 over x dx is divergent. It diverges. Okay, that's the answer for the first one. Okay, the second one we'll consider is we're going to evaluate from negative infinity to 0 of x e to the x. Okay, let's do that. Number 2. Negative infinity to 0 x e to the x. First thing we'll do is say, hey, this is an improper integral. What should I do? I should rewrite it as a limit. So this is equal to the limit as t approaches negative infinity of t to 0 x e to the x dx. Okay, so now we want to integrate this. All right, this calls for integration by parts. So let's consider this. I am going to integrate this by parts, and I'm going to let u equal to x and dv equal to e to the x dx. Okay, so when we integrate this, we get first we have to figure out what v is, okay? Integrate this to get v. V is equal to e to the x. Take the derivative of this to get dx. Okay, so this will be uv minus the integral of v du. All right, and then we can integrate this. X e to the x minus e to the x is what this is, the integral of that is. We're evaluating this from t to 0, the limit as t approaches negative infinity. Okay, let's look at this. First we evaluated at 0, so we get 0 times e to the 0 minus e to the 0 minus, and here's where I'm going to write the limit notation. Limit as t goes to negative infinity of t e to the t minus e to the t. All right, let's have a look at this. Right here, 0 times basically 1 is 0. So we get 0 minus 1 is what we get right here. Minus, okay. The limit as t goes to negative infinity of t e to the t. We'll look at this one closer. Right here, let's take care of this one. Minus e to the negative infinity. This is basically minus 1 over e to the infinity, which is a 0. So we get a 0 there, and this one we're going to concentrate on. So let me just make some more room up here. Let's move it over here. This is 0 minus 1. We have a negative 1 minus the limit as t approaches infinity of t e to the t, and then we have minus 0, so that's okay. All right, so what about this guy? If we use direct substitution, we get, oh, this is a negative thing. We get negative infinity e to the negative infinity. This is basically an infinity times a 0. This is an indeterminate form. And what I would like to do is apply L'Hopital's rule to this, but I cannot apply it in this form. I have to rewrite it so that it occurs in a form that's either 0 over 0 or infinity over infinity. So I'm going to rewrite this real quick. I'm going to rewrite this. So this is me just working on this part right here, okay? We'll stick it back in the rest of this in a second. Let's rewrite it as the limit as t goes to negative infinity of, we could say e to the t over 1 over t. Let's see what this gives us. If we use direct substitution now, this is the same thing as this, just in case that bothers you. T e to the t is equivalent to e to the t over 1 over t, because this is basically a keep, change, flip. E to the t over 1 times t over 1 will give me this back. You can check that out for yourself. This is a way we can rewrite to get it in a form that we can use L'Hopital's rule for. So, right here, what do we get? E to the negative infinity is 1 over e. This is basically a 0. 1 over negative infinity is a 0. So now it's in a form that we can apply L'Hopital's rule. So we'll say, okay, this is equivalent by L'Hopital's to the derivative of the numerator. Okay, the derivative of the numerator is e to the t. Okay, the derivative of the denominator is negative. I should have done this backwards. Now I see. I'm going to rewrite this differently because this is going to be a harder way to go. I'm going to rewrite it to L'Hopital's in the other form. This is the other way I can rewrite it. Now that I'm getting into this, I see this is going to be too painful. I don't want it to be painful. I'm going to leave the t in the numerator. I'm going to rewrite it as 1 over e to the t. This is t over 1 times the reciprocal e to the t over 1. So this is equivalent to this. If I use direct substitution, I'm going to get negative infinity over 1 over e to a negative is really e to the infinity over an infinity. This means I can use L'Hopital's rule. So by L'Hopital's rule, the limit as t goes to negative infinity is equal to the derivative of the numerator, which is 1, over the derivative of the denominator. So I want to think of this as e to the negative t because it's a little bit easier. So e to the negative, then I don't have to use quotient rule. So this becomes e to the negative t times a negative 1. All right, so now we'll apply the limit. If I use direct substitution, this becomes, if I move this to the numerator, this becomes the limit as t goes to negative infinity of negative e to the positive t. Okay. If I use direct substitution and I say, oh, this is really, t is really negative infinity, this is 1 over e to the infinity, this is a big 0. That's what I figured out from all of that work. So basically, I'm going to have negative 1 minus 0, which equals to negative 1. Therefore, the integral from negative infinity to 0 of x e to the x dx converges to negative 1. All right, that was kind of a lot, but there we go. We can figure out infinite limits that way. How about number 3? Let's see what happens here. What about if we're going from negative infinity to positive infinity? What happens there? All right. This is the third type we could get. They say, okay, evaluate this fella from negative infinity to positive infinity of 1 over 1 plus x squared. All right. Dx. here we go. All right, there's infinities on both of the limits. That means I pick some value in between negative infinity to positive infinity. You could pick any real number. Anything would do because they all fit in this category of all real numbers. I'm going to pick 0 because I'm boring. So I'm going to let 0 is going to be where I'm going to split this guy up. So I'm going to rewrite this as the limit as t goes to negative infinity of the integral from t, and I chose 0 to split the guy up, 1 over 1 plus x squared dx plus the limit as t goes to infinity of, I pick up wherever I chose to split it, 0 is where I chose it, to t of 1 over 1 plus x squared dx. And now I just work on evaluating these limits and see what happens. Now, if either one of these diverges, the whole thing diverges. So that's it. But if they converge, we add them together. So let's see what happens here. Let's work on integrating this. Now, this is a form I hope you all recognize. This is the derivative of inverse tangent. So here we go. This, if we take the antiderivative, what we're getting here is the tangent inverse of x, and we're going to evaluate it from t to 0 as the limit as t approaches negative infinity. And over here, when we take the antiderivative there, we still get the inverse tangent. So this is going to be the tangent inverse of x from 0 to t. And this is the limit as t goes to infinity. So let's just look at these carefully. The tangent inverse of 0 minus the limit as t goes to negative infinity of the tangent inverse of t. I only need the limit close to this part because it doesn't apply to a value. It only applies where the t is. Okay. This is the first thing we're looking at, the first limit. And then over here we have the limit as t goes to infinity of the tangent inverse of t minus the limit as t, oh, we don't need the limit on the 0 part, sorry, minus the tangent inverse of 0. Now, when you take the inverse tangent, okay, you're asking yourself, what angle gives you a tangent of 0? What angle gives you a tangent of 0? Okay, so let's think about, this is how I like to think about this one. You could also go to the tangent inverse graph as well, or the tangent graph as well. The tangent inverse of 0, what angle gives me a tangent of 0? It turns out to be 0, and this is because the tangent of the angle 0 is sine over cosine, which is 0. And so we're pulling tangent inverse values between quadrant 4 and quadrant 1, and so it's angle 0 that would give you a tangent of 0. So this is a 0 right there. That means this is the value 0 right there. So right here, let's think about these guys. What angle, if you let t go to negative infinity, then t is negative infinity. So you're asking, what angle produces a tangent value of negative infinity? So if you think of, I use the unit circle. This is what helped me here. What helps me visualize this part better is not the unit circle, but the graph of tangent. So if we look at the graph of tangent, this is what it looks like. This is the y-axis. This is negative pi over 2. This is pi over 2. And it looks like this. This is basically what the tangent looks like. Okay. This is when it's going to negative infinity, right here. It's headed down to negative infinity as it approaches this vertical asymptote, negative pi over 2. So what angle value produces a tangent value of negative infinity is negative pi over 2. So right here is minus negative pi over 2. That's what I get right here. Now, me personally, I like to look at the tangent graph. That's what did it for me. But you could also look at the inverse tangent graph and get that information just by looking at that function itself, which looks like, if you'll recall, it looks like this. It's kind of like this is what it looks like. has these horizontal asymptotes that it approaches as x goes to infinity. So you could have taken that approach. So as x goes to negative infinity, it's going to be down here at negative pi over 2. But however you can see that and get this answer is fine. So if we look at this, as t goes to positive infinity, t goes to what angle value gives me a tangent value of positive infinity, that's going to be a pi over 2. Also, you get that here. As x goes to positive infinity, it's approaching pi over 2. So this one's going to be a pi over 2. All right, that's what we get for those values. So now we just add up our limits. It turns out the first limit did not diverge. We got a value from that. So we'll say 0 minus negative pi over 2 gives me a pi over 2. And it turns out that the second limit did not diverge. We got values out. Pi over 2 minus 0, pi over 2. So together this is pi. Turns out that this integral, we can. Negative infinity to positive infinity of 1 over 1 plus x squared dx is equal to pi. It converged to pi. So that's how you can do one when you have infinite limits at both ends. Okay, so yeah, let's do number 4, and then we'll take a quick break. Okay, number 4. For what values of p does this integral convergent? Is it convergent? So this is something we want to look at and get a little bit familiar with, because it shows up later when we start looking at infinite series. So we kind of want to just get used to seeing this. So that's good. All right. So what we're looking at is number 4. It says, for what values of p is the integral from 1 to infinity 1 over x to the p dx convergent? For what values of p does this converge? That's what we're after. Okay. All right, so here we go. Let us rewrite it as a limit. See what happens. So let's see. This can be written as the limit as t goes to infinity of 1 to t of 1 over x to the p dx. And then we can take the antiderivative of 1 over x to the p, where p is a real number, so we'll let p be a real number. So when we do this, the antiderivative of 1 over x to the p is going to be x to the p plus 1 divided by p, oh wait, this is really 1 over x to the p, sorry, negative. This is, if we think of this as 1 over x to the p, if we think of it as x to the negative p, you can think of it like that, then the antiderivative will be x to the negative p plus 1 over negative p plus 1. We're going to evaluate this from 1 to t, the limit as t approaches infinity. All right, so this is what we have to do. Now you can kind of break this up into separate little cases, okay? One will be where p, here's the first one, where p is greater than 1 is the first case. If p is equal to 1, or if p is less than 1. These are the cases we'll break this up into. So let's consider if p is equal to 1. If p is equal to 1, we're dividing by 0, and this is going to infinity. So this is a problem. So that is divergent. This case is divergent. Does not converge here. All right. Now let's look at this other one. What about when p is greater than 0? Okay, so we've got this limit as t goes to infinity of this. If p of x to the negative p plus 1 over, I'm going to say 1 minus p. Okay, if we've got this. Now, if p is greater than 1, what's going to happen? Okay, let's put a number in there that's bigger than 1 and see what happens. If p is bigger than 1, we're going to make t goes from 1 to 2. Right? If p is greater than 1, then we get the limit, as t goes to infinity, of x to the negative, of t, sorry, t to the negative p plus 1, or 1 minus p, minus 1 to the 1 minus p over 1 minus p. Okay, so if p is greater than 1, then this is going to not divide by 0, so that's fine. But 1 to the anything is just 1, so it's going to be 1 over 1 minus p. Okay, that's fine. What's happening here? Okay, if p is greater than 1, let's say something like it's 4. Then we'd have negative 4 plus 1. What happens there? T to the negative 4 plus 1 over 1 plus 4, basically. Okay. We've got infinity being raised to a negative power. T is basically an infinity because the limit. So we've got infinity to a negative power. We're dividing by infinity to a positive power. This is like 1 over infinity to a positive. So this is going to go to 0. And so this plus some number, this results in some real value. So for the case where p is greater than 0, we find that it converges. Okay, what about when p is less than 0? Let's consider that one. When p is less than 0, what's happening? Okay, we can pick it up right here. This is the same. Okay, for one thing, it's defined because p is not 1. Okay, so when it's, not less than 0, less than 1. So this is defined, so that's okay. So let's pick it up here. We're looking at the limit as t goes to infinity of t to the 1 minus p over 1 minus p minus 1 minus p over 1 minus p, or 1 to the 1 minus p. Okay, this is basically a 1 over 1 minus p. This part starts the same. Okay, that's fine. This is some real number. That's fine. What's happening here, though? Okay, if p is less than 1, then what we get is, let's pick something like 0. Okay, we're going to get t to the 1 minus 0 over 1. Okay, that's fine. But t to the 1 would be infinity to the 1. And so that would be divergent. So in this case, it diverges. If you want to pick something besides 0 just to test it out, that's fine. P is less than 1. Let's pick negative 1. Okay, t to the 1 minus negative 1 would be t squared over 1 minus negative 1 would be over 2. And this is going to be infinity divided by 2, which is still divergent. So we find for this case, less than 1 divergent. For this case, equal to 1 divergent. Where does it converge? It converges for values of p greater than 1. That's when that guy is going to converge for this particular integral. Okay, we're going to take a break and then we'll do type 2.